Or you can start.
Okay, let's take a look at page 88, 89 here. Before we get completely into it here, let's talk about a couple of different things here. If I had the function f of x equals and get your calculators out too.
Which number is this?
It's not one of the numbers. Okay, but have your calculators ready to go here on the calculators or on the graph screen. Just go on the scratch pad, get to the graph screen. If I have this function right here, how many different ways do we have right now of finding f prime of 1, either exactly or approximately? How many different ways could I ask you to find the slope at 1? Somebody give me one. Zooming. And what do we mean by zooming?
Finding 2 points.
2 points really close together. Now we could do that graphically. So we could zoom in with a graph. So we could go in and go ahead and graph that in your y equals right now. Go ahead and graph x squared plus 3x in your y equals. Just go into a standard window. Victoria, you're our presenter. She says, great, I wasn't here yesterday. All right, did you find your assignment sheet? Okay. Everybody else get the assignment sheet? Okay. All right, so we've got x squared. Let's see, I think I have to get the presenter. All right.
Jared didn't.
All right, so we could zoom in, and we won't do it right now, but we could zoom in, and we could get 2 points really close together. Okay, go to the calculator screen. And what could we type here on the calculator screen that would also be zooming? F1, go ahead and type that. We could type F1 parentheses what? 0.999, let's say, let's do 3 nines, okay, and then outside the parentheses, and then minus F1 of 1.001, right, that'd be symmetrical, and then divide that by grab that, and actually you could just grab that answer, that'd be fine.
Or
You can hit a right parenthesis right now.
yeah,
Right.
And then hit control.
Yeah, hit a right parenthesis. Hit a right parenthesis.
Go to the parentheses.
Oops.
No.
There you go. And then just
There you
divide.
go.
And
Now
then
divide.
Control
And then
divide.
left
Or
parenthesis.
you could just little graph.
And then we could go 0.999 minus 1.001, right? And hit enter. There we go, right? That would be zooming. That would be zooming numerically, just by picking 2 points. Graphically would be zoom in, straight line, trace, find a couple points, do the slope calculation. Now both of those are average rate of change, right? Those are approximate slopes of that parabola at 1. Go back to your graph screen, just hit the scratch pad button or go back to the graph screen, and if we think about it, at 1, having a slope of 5 seems pretty reasonable. Okay? What else could we have done? before we get to the instant rate change, what's another way we just estimated the slope? Sketch a tangent line, right? So we have the graph, we just sketch a tangent line and do a little slope triangle, right? Do a little slope. Do a little slope triangle. So if we didn't have the calculator, maybe I'd given you a picture, we could go in there and we could sketch and we could draw a slope triangle. Any other ways we estimated the slope?
Instantaneous.
Actually, the zooming is kind of the secant line, isn't it? I mean, when we pick 2 points, that's a secant line, isn't it? That's touching it in 2 points. And so when we do the zooming and do a slope calculation, yeah, that's the secant line, I would say there. Okay? So then we had our instantaneous rate of change, which was the new one yesterday, right? So we had that new formula, which would be good to just keep up here on the board probably. Limit as h approaches 0, f of a plus h minus f of a all over h. That is the derivative at point A, right? That is f prime of a right there. Okay, I guess I should switch over here. All right, that is f prime of a, and we came up with that yesterday. All right, and that actually came from this picture. For those of you that were gone, that came from this scenario right over here. Okay, so the slope, as these 2 points get closer and closer together, which means as h it gets closer to 0. Okay, and so we have that limit thing. All right, now we also had an alternate form that might be worth mentioning. Okay, we had an alternate form of this, which was the limit. I'm going to change it just a little bit. The limit as x approaches a, I used b yesterday, I think. I'm going to use x today. F of x minus f of a all over x minus a. That's also f prime of a. Okay, again, it's just a slope calculation where the first point is a, the second point I'm just going to call x. I think yesterday I called it b, but I'm going to call it x, and as x gets closer to a, then your 2 points are becoming 1. The key is instantaneous rate of change. We need the 2 points to get closer and closer to being 1 point. All right, so those are the two different, but they're not really different, but the two different, they look a little different to do slope at a point. All right. There is some other notation for derivative that I want to talk about, but we'll get into that. We'll get into that here a little bit later. So let's get to the homework questions then. It looked like a lot of people were asking about 34 and 35. 43 and 44 were pretty popular. What were some before then, though? That we do have time to do maybe 1 or 2 that were before those. Number 7. What did you guys get for an answer for number 7? -1. You're not getting -1 on number 7?
Oh my God. That'd be nice for everybody.
You thought it'd be nice to see that again, huh?
Yeah.
All right. Well, we are going to go through those plenty.
Okay.
So I might not do that. But thanks for asking, Harry. And I appreciate you thinking of everyone. But we are definitely going to go through this long form of this plenty here today. So any others? Any others besides that
29.
kind of form? 29.
Yeah.
Carefully explain each step. Okay. Now, on 29, and this is good because it kind of relates to the question Harry was asking, is this is going through. They go through and go through the steps you would do for f prime of 3. But now what do they want then? Okay? Well, here's what I think would be a pretty good answer. In A, all they're doing is plugging a 3 into the definition. Plugging a 3 in for A. Okay? In B, They're just doing that function notation. In other words, if I tell you what's f of 2, you're going to take 2, plug it in for the x. If I say what's f of 7, you're going to take 7, plug it in for the x. In line A, they say f of 3 plus h. So you're going to take 3 plus h and plug it in for the x. So 3 plus h plugged in for x would be 3 plus h squared. Minus f of 3, plug a 3 in for the x, you get 3 squared, which is 9. So that's all that happened in B. They plugged in 3 plus h and they plugged in 3 into the function. In C, they just FOIL and simplify. In D, they factored out an h and canceled. And then in E, they plugged a 0 in for h. And that's the key step, because plugging a 0 in for h is letting the 2 points become 1. The limit as h goes to 0. And so the answer, final answer is 6. Okay, so that would be my explanation of what was happening there. Okay, I guess I was thinking about 11. An average rate of change, maybe that was not a big deal. I just wanted to emphasize again, in 11A and B, the average rate of change is just the slope between the endpoints, so that's just a rise and a run on the graph. And in C, the instantaneous rate of change would be a tangent line. You would just put in a tangent line there and do a little slope triangle. Okay? So again, emphasizing that difference between average rate of change and instantaneous rate of change. Well, let's jump into number 34 then. This is something that over the next 3 or 4 days we'll be looking at more and more, but they give us this problem here. The limit as delta x approaches 0, delta x is the same as what here? H. Okay, delta x is just another name for h in this. Delta means change. The Greek letter delta is change in x, okay? And that's really what we have. That's what h is. We go from an x coordinate here to another x coordinate over here, and delta x is how much we changed. H is how much we changed. Okay, minus 3 all over delta x. Now what's the key here is the recognition. You need to recognize this as this. But what we're doing is we're really working it in reverse. Okay? So instead of taking our function and our a value and plugging it into this, we're starting with this, and they want you to say, hey, what was the a value and what was the function that caused it? Caused it this. Okay, well I think that the secret to working these back is this first term right here, f of a plus h. Okay, because remember what we just said a minute ago with the 3 plus h. What you're going to do is you're going to take a plus h and plug it in where the x was. So when I look at this problem and I see right here, that looks like the a plus h to me. That must have got plugged in where the x was in the function. So what's that tell you the function must be? Square root of x, because the a plus h got stuck where the x was. And what's the a? Got to be the 9. Now then, you always double check with this one. If the a is 9, then f of 9 in this function would be square root of 9. Oh yeah, that's 3. Okay? So there we go. So what this problem should be doing is finding f prime of 9 on the square root graph. Right? That's what this should be doing, because this is f prime of a. Our problem a is 9. So this value, whatever it is, should be giving us that. Well, the square root graph is what? What's that look like? Upside, or a sideways parabola. It's the top half of a sideways parabola. And at 9, we would expect to have a pretty flat slope. Okay? Now, here's the part I'm not sure everybody knew for sure what to do. You may have gotten this far. But it says, estimate this value. You're not supposed to go through the whole long algebraic way of doing this. There would be a way we could do it. But you were supposed to just graph the difference quotient. Now remember, let's use a little blue here. This part here is the difference quotient. Okay? This part is the difference quotient. It said to graph that and estimate the value from there. So go to your graph screen on your calculators. Okay, go ahead and you can clear that one out, Victoria, out of F1. And what we're going to do now is we're going to graph the thing in the blue. Now, whenever we draw a graph of something, we're not graphing square root of x now. Understand that. We're graphing this. Well, we can't put in delta x as our variable. We have to put in x for our variable, right? So instead of delta x or h, we're going to use x. So go ahead and plug this in. Square root of 9 plus x. And then outside the parentheses, subtract 3. And then x underneath. And go ahead and graph that. Okay, now, what we're interested in, okay, there's our graph. We're interested in this value as, now remember, we're not using delta x now, we're using x, right? We're interested in this value as x is getting close to 0. Well, where's x getting close to 0 here? The y-axis. So we're interested in the output at the y-axis. So do a trace at 0. Do a trace when x is 0. What do you get? Oh. Did we expect that? Oh, sure we did. When x is 0, we get square root of 9, which is 3. 3 minus 3 is 0, divided by 0. We get 0 divided by 0. Oh, yeah, that was that thing we were doing yesterday. We were getting the h's to cancel and so on. Oh, it is undefined. We'll just trace back to the left then. 0.168. Trace to the right. 0.165. Now, something that will come up when we go over our quizzes and will become more important as we go along, as we start using our calculators more. You know, we've been doing some estimating off graphs, so it hasn't been an issue. All of your answers must be accurate to 3 decimal places. And you cannot round. I mean, so if I was going to give an answer right now, I do not have an answer to 3 decimal places. On the left, it was 0.168, and on the right, it was 0.165. So I should zoom in. So let's zoom in one time here. Okay, and just zoom in right at the y-axis there. Okay, zoom in a couple times just for good measure. Okay, trace at 0 again now. Yeah, I could have done the trace step. Yep, I could have done that too. Okay, trace to the left a little bit. 0.168. No, that's not enough. You count. I'm doing this on purpose a little bit. Right now, I'm tracing in a fairly clumsy manner by doing the zoom in, zoom in, zoom in. It's a little longer than it needs to be. What could I do on the calculator screen right now?
Trace down.
No, that'd be on in the width graph screen. I could do the trace step. Go to the calculator screen. Right now, couldn't I just go F1 of 0.00001? Right? Something really close to 0.
What we did before.
Okay? Yeah. And hit enter. Okay? All right. Now I feel pretty good about, you know, I could do some more O's, whatever. But it looks like 0.16666 may be repeating, which is actually 1/6 as a fraction, and that is the answer, 1/6. And doesn't that make sense that we get a pretty small slope, positive, okay? But that's what that was doing. So 35 is the same thing. Now 35 was a little trickier in from the standpoint that on 35 you have limit as h goes to 0, cosine h minus 1 all over h. Now again, I'm looking for the a plus h that got plugged in where the x was. Well, what must the a plus h be to have just an h? 0. So really what this is 0 plus h minus cosine of 0 all over h, because what's cosine of 0? 1. And so what is my a on that one?
0.
0. And my function?
Cosine.
Cosine of x. And so what this is looking for is the slope of the cosine graph at 0. Well, it should be what? It should be 0, right? It should be 0. And so if you repeat that and you graph it, it should be crossing through the origin, whatever this graph looks like. If you graph this graph, but again, you graph cosine x minus 1 all over x, and you'd see what it looks like as x is getting close to 0. Just another way to evaluate these limits, and we're going to do some more work with this later on, but another way to evaluate these limits other than that long algebraic way we did is to just graph this part and see what's happening as that input gets close to 0. And see what its output is. And that's another way of doing it. Okay? All right. So that's 34 and 35. Let's take a look at 43 and 44. I'm actually going to save 43 because we're going to do one very similar to that. So let's do 44. All right. So we've got f of x equals 2 over x, and f prime of 4 is what we're looking for. All right. So if you were gone yesterday, what we did is we said we're just going to, and this is like number 29. It's going to look a lot like number 29 there all written out. This is like Harry was asking on number 7. So what we had to do on that one. We're going to write out the long definition here of the derivative. So f prime of 4 is limit as h approaches 0, f of 4 plus h minus f of 4 all over h.
Your name is missing from this
Okay.
There's
All right. So what's f of 4 plus h? I suppose I better get some color, huh? The blue thing is 2 over 4 plus h. That's the blue thing. Minus, did red work yesterday? Yeah. The red thing, oh, well that's disappointing. Okay, whatever. Minus what?
2 over 4.
2 over 4, right? We're just plugging in and getting those two pieces here. All right? Don't forget all divided by h. Okay, so there is some algebra. There's several algebra things that we are going to have to really get good at in the next week. One is foiling and simplifying and canceling. One is common denominators. And another one has to do with number 34 where we work with radicals and something called the conjugate. Those are 3 algebra techniques we're going to have to do a lot of. Here we need to get common denominators. Mrs. Payne always calls this bow tie.
why.
Okay, I don't know. Well, because it kind of makes a bow tie. Essentially, to add 2 fractions, let's try one here. Off the screen.
Yeah.
Okay. If I had to add 2/3 plus
You're on.
You're off the screen.
4/5, if I had to add 2/3 plus 4/5, I can take the 3 times 4, right? And that would be, well, first I take 3 times 5, which is 15. That'd be my common denominator. 3 times 4 is 12. 2 times 5 is 10. I get 22 over 15, right? And 1 7/15 or whatever. Okay, so you multiply the bottom 2 to get your, I guess that's a bow tie, I don't know. That's what she calls it. But essentially, another way of thinking common denominator that, you know, the way I always think of it is the common denominator is 15. So this one needs a 5, so I just take top and bottom times 5. This one needs a 3 to make 15, so I multiply top and bottom by 3. So I get 10 plus 12 all over 15. Same thing. So this one needs a 4, top and bottom. This one needs a 4 plus h, top and bottom. My common denominator will be 4 times 4 plus h. Now a little hint here on these problems with a common denominator, don't distribute through the denominator. leave the 4 and the 4 plus h alone is usually a good idea. Leave it in its factored form. On top, though, you do want to distribute because you're going to be subtracting and simplifying. So you get 8 minus, and then here you'd want to distribute, so you'd have minus 8 minus 2h. And make sure you get that negative on there. Make sure you distribute through that negative. Okay, this would be 8 plus 2h, and you distribute the negative, it'd be minus 8 minus 2h. Now, the nice thing that happens, one of the nice things, that h's cancel. Now you've got a complex fraction, a fraction within a fraction. How do you deal with that? Multiply by the reciprocal. You got h down here, multiply by 1 over h, right? And that'll take care of that down there. All right? So that's just a 1, so we can ignore that. So now on top we have negative 2h over, and then the bottom is a 4 and an h and a 4 plus h. What can you do there? I wouldn't distribute because we can cancel the h's right now. See? That was the reason I didn't want to distribute that in the first place, because I'd end up just factoring an h back out anyway. So, and that, remember, yesterday was the good thing that was happening to us, is when we could cancel those h's, because don't forget, I got lazy here, I quit writing it. We're doing the limit as h goes to 0. Well, if I put a 0 in for h, that makes that be 0 divided by 0, which is undefined. Now that the h is canceled, I've got negative 2 over 4 times 4 plus h. Now I can put a 0 in for h. So I get negative 2 over 16, and in other words, as h gets really close to 0, this 4 plus h gets really close to just being 4. 4 times 4 is 16, which reduces to negative 1/8. If I hadn't factored or distributed through the negative, I'd have a positive right here. And if you look at the graph of 2 over x, keep in mind that's what we're doing here. Don't forget the big picture. The big picture of this is we've got this graph 2 over x, which looks like this, and we're finding the slope at 4, which would be out here. It better come out negative. Okay? And so, and it did. Came out negative 1/8. All right, so that's an algebraic technique that getting common denominators we're going to have to be able to handle. All right, so that's a lot like number 7 dealt with. Number 44, we've got that there. Okay, let's move on then. Well, wait a minute. 46 was kind of interesting and would be worth mentioning here. On 46. Suppose that f is decreasing and concave up on the interval 0 to 10, and m is a slope between 3 and 5. So if I have a graph, here's 3, here's 5, and this graph, what's it? Decreasing and concave up. So the entire time it's like this. Decreasing and concave up. M is the slope of the line through this point and this point. So here I've got a line, straight line, that goes through there. M is that slope. Is M less than the slope at 3? So a picture is what you'd want here. So here's the slope at 3. Now keep in mind they're both negative. This always makes more sense to me if I put numbers on it. So the red one, let's pretend that the red one is a slope of negative 1. What would the green one be in relation to that? More negative. As in negative 1.5 or negative 2 or something like that. Okay? So is negative 1 less than negative 2? No. Right? I mean, because that whole less than thing gets muddy when you're talking about negatives, right? The slope at 3 is steeper. Okay? Negative 2, but is negative 1 less than negative 2? No. Okay? So, and then how about at 5? The slope at 5 would be more like what? Negative 1/2 maybe. It's not as steep at 5 as the red line. So it's a lesser number, but it's actually bigger value when it comes to, because of the negative. So is m, in other words, is -1 greater than -1/2? And the answer is no, it's not. Okay, they switched it around us right there to negative. So justify with words and picture. But again, the point being that as that thing curves, those slopes are changing. The slope between there is getting less and less steep as we go along. Since it's negative, it's actually getting bigger. The slope's actually getting bigger as a value, but it's getting less steep as far as that goes. Okay, so that's what was going on with that one. Okay, turn to your notes then, and here's where we're going to head next with this as we go over to section 2. No. Well, sort of. Sort of. We're going to do 43, except without a 4 plugged in. We're going to do it with an X plugged in, which you'll see here in a second. Okay? So, all right. Yesterday I had this picture. And we labeled the point A that we were looking for the slope at, and we labeled a second point A plus H, and we let the 2 points get closer together, which we said was accomplished by letting H go to 0. As H gets very small, and that's where this formula comes from right here. So as H gets close to 0, the 2 points become 1, and that's how average rate of change, or the secant line, turns into the tangent line. And there you go. Now, we're going to do the very same thing, except I'm just going to change my label a little bit. All right? So if you want to redraw the picture and so forth, that's totally up to you. But all I'm going to do here is say I'm going to change that to X. Now, what's the big deal? Well, typically when we use a letter like A in this, we're referencing a specific X value. But when we use the generic X, we're saying we're using that to represent all the X values. So what we want to get to now is, instead of finding the slope at a specific point, we want to find a slope formula for all the points. Now, a few of you have come to me already with your guesses about what you're seeing on some of these slope graphs. Like, for example, the parabola graph derivative always seems to be what? That's a line, a diagonal line, doesn't it? Right? A parabola graph always seems to have a line for its derivative graph, and so forth. Well, the same thing's going to be with equations. Okay? If you have an equation for an F graph, then there's going to be an equation for the F prime graph. So our job here in Chapter 2 is to begin the process of finding out what those equations are. We're actually going to start it today. So if I have an F equation, what's the F prime equation that goes with it? Well, the only thing we know about finding slopes at this point, exact slopes, is this formula right here. So we're going to use it. But instead of finding slope at a point A, we're going to find it for all points X. So it's just a minor kind of difference. So everything else should be the same. We'll create a second point X plus H. Okay? Oops. We'll create a second point at X plus H. We'll draw in our tangent line. We'll let H get closer and closer to 0, right? And the slope of the green line is just going to be this right here. So from this point forward, when I write the definition of the derivative, you're going to pretty much see me write this form here instead of the one with the A, because this is more general purpose. All right, so F prime of X equals limit as H approaches 0 of F of X plus H minus F of X all over H. Okay, there you go. That's our more official definition of the derivative, the one that I'll use. Now, it works both ways. If I want to do F prime of 4, F prime of 4 would mean I just plug a 4 in place of the X. Plug a 4 in place of the X. Both places, just like I was plugging a 4 in place of the A. Okay, so nothing has changed as far as that goes. The difference is we won't come out with a number answer at the end. I mean, if I do f prime of 4, we will, of course. But what I'm going to say is let's just do f prime of x. Let's just find out what f prime of x is with x's in the problem. All right? So we're going to go ahead and do that with the function f of x equals x squared, our simple parabola. All right? And we know that it has a graph that looks like this, right? And what do we think the f prime graph should look like? A line going through the origin, going up or down? It should go up, right? It should, because we have negative slopes in the beginning, but getting less negative. So, oops, goes through the origin. Negative and getting less negative, and then slopes here that are positive and getting more positive. So we think we're going to have something that looks like that for f prime based on the work we did back in chapter 1. Okay, so here we go. Let's do our definition. So if f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So the next line, limit as h approaches 0. What's f of x plus h in this problem? X plus h squared, right? We take x plus h and we plug it into the function for x. Minus, what's f of x? No, that's just x squared. All over h. Next step is FOIL. What do we get if we FOIL that out? X squared plus 2xh plus h squared minus x squared all over h. Some nice stuff happens with the x squareds canceling out. We can factor out a h, 2x plus h all over h. H's cancel, leaving you 2x plus h. The limit as h gets closer and closer to 0 is 2x. Think about what we just did. We just did our first derivative formula. And doesn't that fit with what we thought the graph should look like? Y equals 2x. What's the power in having f prime of x equals 2x? We can find the slope at all the points now instead of just at one point. We don't have to go, like yesterday we did x squared plus x, we did f prime of 3, and then we did it again for f prime of 2, and then you guys did the homework for f prime of -1, right? We had to go through it every single time. We go through it once with x, now we have a slope formula, the derivative equation, and now we want the slope at 2. We want f prime of 2, we put a 2 in for x. We want f prime of 4, we put a 4 in for x. Okay? All right. Let's try another one. Hey, that's a great idea, Jacob. Let's do that. The guy's being disconnected from the mothership. All right. Oh. F of x equals x cubed. We're going to have a problem there. All right. F of x equals x cubed. We want f prime of x. So we start with the formula. I really think it's helpful to write down this first, just to keep reminding you it's not critical. But if you're having any trouble with it at all, that's a good idea. All right, so the limit as h approaches 0. So f of x plus h, and this one is x plus h cubed minus x cubed all over h. Now my guess is some of you have a feeling you already know what this is going to be. Don't say it. Don't ruin the surprise. You have a feeling what this is going to be already? Okay. But it's all right. What's x plus h cubed?
X cubed.
You ever hear of Pascal's triangle?
Yeah.
Yeah, but
No, we have.
But nobody memorized it. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Well, there's nothing really memorized, but you just add these, right? But what's important about those?
That's the pattern.
Coefficients on a binomial expansion. So x plus y to the 0 is just 1. X plus y to the first is 1x plus 1y. X plus y to the second is 1x squared plus 2xy plus 1y squared. And x plus y to the third is 1x cubed. So let's write it down here. Limit as h goes. Now, otherwise, you can do x plus h times x plus h, FOIL it, and then take that times x plus h and distribute everything, and that's fine. But you get 1x cubed plus 3, what? X squared h plus 3 xh squared plus 1 h cubed. And there's that pattern with the powers. It goes x cubed, x squared, x to the first, and then no x's, and the h's go in reverse. And that's a binomial expansion. So if you had to do x to the fourth, x to the fifth, x to the sixth, this would be nice to know. Okay? All right, and then minus x cubed, don't forget then the minus x cubed. All over h. On the quiz, I'm not going to make you do x to the fourth, x to the fifth, or any of that stuff. Okay, but you might have to cube something. If you just have to FOIL it out, that's what you do. All right, x cubes cancel out quite nicely. Which then leaves us with being able to factor out an h, correct? Take out an h, you're left with 3x squared plus 3xh plus h squared. All over h, the h's cancel, which is the thing we're hoping would happen. Leaves us with 3x squared plus 3xh plus h squared. What happens as h approaches 0? As h approaches 0, that term will go to 0, that term will go to 0, right? And you'll be left with 3x squared. If you didn't see the pattern before, maybe you see it now. If f was x cubed, f prime is 3x squared.
Now, if f was x to the fourth, would it be 4x cubed?
If f was x to the fourth, would f prime be 4x cubed? And the answer is yes. So, this rule is called the power rule for derivatives, and it will be the first of many derivative rules that we will learn. So, if f of x is equal to x to the n power, then f prime of x is n times x to the n minus 1. That is called the power rule for derivatives, and it works for any polynomial, any monomial. Okay, we just showed it with a couple. We could actually prove it. And this is what I was talking about with number 43 in the homework. Number 43 looks just like this, except you had plugged a 4 in instead of the x, okay? And so you foiled it out and did your thing there. Okay? All right. So we have our power rule. Now what happens if... All right, I think I can get rid of this. What happens then if we take a power like an x squared or x cubed, or we shift it around? And you had some of those in your review problems before our last quiz. So let's look at a couple of those. What if we had f of x equaled x to the 4th plus 4? What if f of x equaled x to the 4th plus 4? Well, f prime of x, think about what that plus 4 does. Shifts it up 4. Now, does that change the slopes? Does it change where the slopes happen
Yes.
if you shift it up? Right? The slope at 1 on the x to the 4th graph would be the same as the x to the 4th plus 4. So what should be the derivative then of x to the 4th plus 4?
4x.
It would be exactly the same as if that plus 4 wasn't there. Now remember when we had f prime graphs and we drew f graphs, and we said there's an infinite number of vertical shifts, right? Well, this would be an example of that. The 4x cubed graph, as an f prime graph, would have x to the 4th plus 4 as a possible f graph, x to the 4th minus 7, x, right? All those that were vertically shifted would work. Now another way to think about this, and this is a rule for derivatives, is if you add a bunch of terms together, it's legal to just do the derivative of each of the terms. So another way to look at this is say, well, the derivative of x to the 4th is 4x to the 3rd. What's the derivative of 4? Well, what's the graph of 4 look like? Horizontal line. What's its slope? 0. Another way to think of it is this. X to the 4th, or excuse me, 4 could be thought of as what's that? You have a question?
No.
Oh, okay. 4 could be thought of as 4x to the 0, right? Because x to 0 is just 1. Do the power rule on that. Bring the 0 down in front, which of course would make the whole thing 0, right? So the derivative of a constant is always going to be 0, right? And so that's just an automatic. So we don't even have to think about that. So that would be another way to do the derivative of that. Instead of thinking of the shifting thing, just say, hey, derivative of x to the 4th is 4x to the 3rd, derivative of 4 is 0, and just be done. Okay? All right, let's try another one. What if we had x plus 7 to the 3rd power? Now what's the plus 7 do? Left 7. What's that going to do to the slopes? It's not going to affect the slopes other than they'll happen at a different place on the graph. 7 to the left. So, what's your guess is what the derivative will be here? 3 times x plus 7 quantity squared. The rule still applies. We'll bring the power down in front, drop the power by 1, but the shift left or right stays in the derivative. And it makes sense. If the original graph is shifted left 7, all the slopes get shifted left 7. Okay? The lesson from that will be the inside doesn't change. when we do the power rule, if there's stuff on the inside of the function, it doesn't change. All right, let's try this one. What if you have a 5 setting out in front? What if you take the parabola x squared and you put a 5 in front of it? What's that do to the graph? Vertical stretch by 5. Now that certainly has to affect the slopes, right? What's that going to do if you make all the y values 5 times as big? Aren't the slopes going to be 5 times as big? Because if you go over 1 and up 1, now you've made the y values 5 times as big. Instead of going over 1 and up 1, you'll go over 1 and up 5. So you've changed the rise by a factor of 5. So it seems like the 5 will still be hanging out there. The 5 will still be a part of the slopes. You're going to have to multiply the slopes by 5 too. And then we would do our normal power rule. Bring the 2 down in front, drop the power. So your answer will be 10x. So the lesson to learn there is, and it makes sense with slopes, is you got a number just sitting out in front of a function. It just stays there. You do your normal power rule. You bring the power down in front, so forth. Okay? Another question. Does it work for negative powers? Right? Does it work for negative powers? And the answer is yes. But you got to be careful. What would that be? Negative 2x to the negative third. Because you subtract 1. So you take negative 2, subtract 1 would be negative 3. So negative 2x to the negative third. And it's okay to leave your answer as a negative power. That's fine. Okay? So it works with negative power. Does it work with square roots and so forth? And again, the answer is yes. X to the 1/2. That's a square. So that's one of the reasons we learn about radicals, changing them into fractional powers, because in derivatives, we want to work with powers because this power rule is so neat and handy and easy. So any radicals we have, you know, we want to change them into fractional powers. So this would be what? 1/2 x to the negative 1/2. So you're going to have to be able to add and subtract fractions and so forth. At least be able to subtract 1 for this power. What if I gave you then 4th root of x cubed as a function? That's x to the what? That's x to the 3/4. The root is the denominator, the power is the numerator. So the derivative would be 3/4 x to the negative 1/4. 3/4 x to the negative 1/4 would be your derivative. Okay? So we stretch, we shift, we have radicals, that kind of thing. We should be able to do that. All right. Give you some work time here. Your homework is a couple of part of the book and just a couple problems I'm going to give you. I want you to do. I want you to do by the definition. Oops. By the definition, I want you to find the derivative of 1 over x. I want you to find f prime by doing it out the long way here. Okay? And that's going to involve a common denominator, just like we did on number 44, so we need to practice that. And I want you to do square root of x. Now we know what the answer should be by the power rule, right? Because we know this is x to the negative 1, and we know this is x to the 1/2. So we know what answers we should get at the end. But I want us to be able to get them by going through the long way. I guess this would be the short way now, right? This would be the long way. Okay? So you're going to do each of those. Those would be good ones to do here first. And then And I can help you with those if you've got, and then, whoops, not 2.1, 2.2. We're gonna start with 17. I think these are on the assignment sheet, but I did take off a couple of them here, so I changed a few things. 17, 19, and 20. 23, 33, and 35. 36, 39, 45, and 46. So I took a couple off the front end and one off the back end, I think, on there. And those are in section 2.2. Most of those deal with using the shortcuts. Okay? And on some of them, you have to first, FOIL, before you can use the power rule, like somebody on this one might have cubed this all out and then done the power rule. You could have cubed that out, right, with FOIL a couple times and then done this, or then done the derivative, and it would look different than this, and that's okay. Excuse me. So on some of them, they're going to have you simplify them algebraically first, so you can then use the power rule. But you're going to be using the shortcut quite a bit on the book assignments. And then when it asks you to do the second derivative, what do you suppose the second derivative of this one up here would have been? Here's the first derivative. What's the second derivative? 12x squared. Because the second derivative is just the derivative of the first derivative. Okay? So to get f double prime, you just do the power rule again. Okay, so on some of the problems, they have you do f prime, and then they ask you to come in and do f double prime. So those go pretty fast.
So what would be the equation for that one?
We wouldn't even write it down. I mean, I guess, well, because it's just the same thing. To go from f prime to f double prime, you just pretend this is f prime, this is f double prime, just like the chart. It's just the same thing. I mean, I guess what would you do, Jacob? You bring the n minus 1 down in front, and this would be n minus 2. You'd have n times n minus 1 times x to the n minus 2. But I've never thought of a time where that was necessary to know. So just do the derivative once and do it again. I guess you might think it might save you time to go directly to the second derivative, but yes, you may. All right, so here's your pattern. Here's what the first couple are looking like with the 1 over x and the square root of x. When you get to the square root, if you need some help with